Okay, today we are going to talk about irregular waves. You may also call this to be realistic sea waves. Or ocean waves maybe. Sometimes it is also referred to as random waves. You can call by any name. The question that we are going to answer today is this: if you went to an open ocean, if you were to put a stick and measure the wave heights, you are not going to find very nice a sine curve, okay, which is what we have been always talking earlier, irregular waves. What you will find? Some kind of random thing, something like that. I mean, if you put a stick in ocean, you are going to find a record which will look a long random, say against time, the height, it will look like that. In fact, if you were to take a snapshot, a photograph, you will find the similar kind of random nature along spatial dimension. That is, it can also be a similar nature eta and x. Okay. Now the question is this: see, the open ocean waves or the realistic ocean waves do not resemble or do not look like a nice simple sine curves. They look completely random in nature. You seem to think that there is no correlation, etc., etc. And it is this environment on which I am placing my object, the ship or offshore structure or whatever. It is these waves which acts on the ship, and I need to figure out, or we need to study how a ship would respond to these waves, not to sine waves as such, because it is, anybody will question that, well, when I go to ocean I do not find any waves which is sinusoidal in nature. So therefore, today what we are going to talk, how do we represent these waves? How do we classify these waves? How do we characterize these waves so that I can study tomorrow, it means subsequently, what would happen when I place a floating vessel like a ship on these waves. Okay. So this is a question that we are going to answer today. Now obviously, when a signal is random, supposing I take t versus, well, let me take t versus eta. So the graph will typically look something like that, Now what we could do, see, is that we could analyze these waves. This is a random signal, irregular signal. We can analyze them statistically. For example, I can define crest to trough as height, okay, wave height, say HW. Now you take a long signal and measure all this crest to trough, etc. What would happen? You are going to find that this HW, which I am defining as crest to trough or trough to crest, peak to peak, you may say, there are a whole lot of occurrence, like you will find first record shows 3.1, next one shows 2.1, next one shows 3.0, etc., etc. So you are going to get a whole lot of random record of heights, so many heights there. Okay. Now what we can do is to make a statistical analysis, how many heights occurring how many times in a signal. This is what we can call a histogram. Now typically what would of course happen is that you would not be able to find out exact value. For example, I may have this first one in this example, say I just put some number 0.37, next one maybe 1.15, next one may be 3.95, next one may be 0.98, maybe 2.15, like that. Now, you know these heights like that occurring say 1000, 10,000, whatever. Now, the question is, obviously you cannot pinpoint the exact numbers, because up to second decimal or third decimal the numbers won't repeat. So, what we will do, we will make a class chart. 0 to 1 meter, how many times it occurred? 1 to 2 meter, how many times it occurred? 2 to 3 meter, how many times it occurred? Okay, we could make something like this. Now, like we can analyze this quantity statistically, but before I do that, let me find out other terms that exist. Okay, see, height is one parameter, it only tells me this crest to crest. What about this side? It does not have any measurement of this. For example, if I stretch this full thing, I pulled it this side, keeping the height same, I would still have a height statistic same, but the signals are not same. For example, if I took say this, I just made it, for example, I just stretched it, the heights will be same. So, obviously height, which is a measure in the vertical direction, does not say it all, because there are other parameters. Now, if I were to now measure something this side, what is this side? Period. So, what we could do here, again period. What is a period? If you know in sine signal, it is repetitive, crest to crest or trough to trough or 0 to 0. So, here what we could, again it is not all the same thing. For example, if I were to take the period time interval between crest to crest, this is my crest to crest period. See, here to here, here to here, etc. I define this as Tc. In other words, I will write down, first let me write down this h, let me, okay, h. This is actually peak to peak this is one measure. Now, remember when we talked about regular waves, we always talked in terms of amplitude, not height. Okay. When we talk of regular wave, you know, we have this A cos, and A is nothing but h by 2, but we normally use the term A, amplitude. What is amplitude? Measure of the crest or trough from the mean level, agreed. But in irregular signal, what happened? This mean level is not known. You see, you do not see it. You put a record, you are going to only find this graph, you do not actually find this black line. The mean level is not known generally. That is why it is a convention to use peak to peak, because you do not have the mean level from which you are drawing this line. All you are getting a record of this black line. That is why in random signals you normally use peak to peak. You do not use amplitude but height. That is one thing. Now, coming to the period side, this side, I can have one period Tc, which is, well, when I measure the time interval between successive crests, this is called crest to crest period. Now, the other thing, well, of course, you can always say I can have a trough to trough period, normally not used. Other period very important is what is known as taking time from here, where the signal has crossed, well, here I need to have this 0 line from some reference, here, well, in this case to here, that is when the signal crosses the level 0, if you can draw a 0 line, then the time interval from first crossing of 0 line to the next crossing of 0 line, this is known as, in fact, 0 up crossing period. Up crossing, it is crossing upward direction. So, this is called 0 up crossing period. You can always say there should be a 0 down crossing period. My point is, therefore, even when you define period, there is nothing unique. It can be crest to crest, it can be trough to trough, it can be where it crosses upward to next upward, downward to next downward. Typically, the crest to crest and upward to upward is used to characterize. You cannot use all, so many of them. So, Tz I will call it. Now, this is with respect to time. Supposing I were to take a signal, a photograph at one point x, and I find this eta, again I will find this random something, this is my x distance, remember. So, here obviously the measures are lengths. So, similar way here to here I will have what is called peak to peak length, LW, or no sorry, peak to C, that is crest to crest length. Similarly, I will have here to here 0 upcrossing length. I will call this Z. This pen is not. Or if I, this is going to be 0 upcrossing length. So, what we are finding out is that when it comes to this horizontal axis, whether it is time or whether it is length, means space dimension, I can have different kind of lengths or periods. In the vertical direction, I normally have only one, that is HW, peak to peak height. Okay. So, these are the various parameters for trying to characterize a random signal. Random signal means everything is basically random. I like to give an analogy. You see, when you are doing ship design, ship hull, what we do? We try to characterize the hull by line span, but otherwise we have some fixed number like block coefficient, waterplane area coefficient, etc. Remember that all of this, even if I have 4, it is not unique, because I can always have a different, slightly different line span for with the same values. But what you do, you try to have some fixed set of numbers, trying to characterize something that can be, have a wide variation. So, similarly for a random signal, we like to have some of the numbers. These are the typical one. For period, it is crest to crest or 0 upcrossing. Length also same thing, height is peak to peak. Okay. Now, let us look at the height. The height is the most important one, because I will come back to this diagram again, this one, because everybody knows that higher the wave, more severe it is. You will call that, we always talk in a loose term that waves are so high, 30 meter high, 20 meter high. I mean, height is a measure of severity. Okay. Stronger storm will give a higher waves, etc., etc. So, height has, well, we also know that energy of a waves is proportional to square of height. So, height is a measure of the energy of the waves, height is a measure of the severity, etc. So, height becomes typically more important to characterize waves. Now, coming back to this, now we have a long signal, number of heights occurring, 1 million, 10,000. So, as I said, you made some kind of a histogram. What we do is that we will try to figure out in cluster how many waves between 0 to 1. Well, this can be any interval 0 to 1, 1 to 2, etc. Let me go to another diagram, but we kind of make something like that. See, let us say here heights and occurrences. So, you have say in interval 0 to 1, 1 to 2, like that, say, etc. And you have these occurrences here. Okay. Now, of course, what we can do, these are, we can say heights, let me call this to be HIs. This is, and this is occurrences, numbers. Let us say whatever number in I. So, if I do that, total signal is like this. Okay. As I said, why you do this cluster? It is not necessarily 0 to 1, it can be 0 to 0.1 if you want, 0.1 to 0.2 if you want, but a cluster. Now, when you do that, when you plot, obviously I can actually have here a percentage occurrence simply by taking here as Pi as defining at Ni by N into 100. It is all simple, no, like the percentage occurrence I can do that if I want. So, I can actually have it what is known as histogram. Well, I can plot here Pi versus this Hi. So, if you do that, it looks something like everybody knows this. The total area is equal to 1 if I take probability, etc. Everybody knows this is actually, I can call this to be probability function also, Fx. This is a typical histogram. Now, here comes the question. Now, of course, from this histogram, I can find out the values of average. What is average height? For example, H average. It is simply going to be that Ni into Hi divided by, like N, right? Something like that. Okay. So, what I am trying to say is that all this we know, the average value, etc. Now, the question, the most important question is like this. Of course, if I know this function, if I actually call this, if I were making this much smaller and smaller, it is approaching a statistical function, and from suppose I call this Fx, then I can find out any quantity, something like what is the probability, for example, of say some value, say H, W exceeding some given value. It is going to be simply a to infinity of Fx dx, etc. It is very simple, right? I mean, what is the chance that the wave height is more than this? Well, you can find the statistical distribution. We will do some example for that, etc. Average, you can always sum them up and find average, etc., etc. Okay. So, there is no problem on that. Basically, what we are doing, we are trying to find out the number of occurrences, plotting it, the plot will be an Fx curve, and then from there I can find out average value of exceeding some given wave height, and all quantities that I want to know. Okay. Now comes this question, now people have been doing this for years together. Oceanographers' job has been to characterize ocean waves. So, they have been collecting data and plotting histogram, not only for wave heights, also for periods, etc. The amazing thing, interesting thing is that when you keep doing that, it turns out that this graph tends to follow a theoretical Rayleigh distribution. Now, let me draw one more one. In other words, if I were to do this P of, let me call it now P of H, because this is what it turns out to be versus H. It turns out that if I were making histogram and of course making a continuous graph, it is following a theoretical you see. What is the difference between this? Of course, for this the formula, I will write the formula later, but let us just describe the slightly character-wise. Now, supposing I ask your class, tell me your ages. So, what will happen? Somebody will say 20, very fine graph, 21 years, 2 months, 19 years, 4 months, etc., etc., right? So, if I make an average and if I plot, you will find out mostly it will be a normal distribution. Now, the normal distribution or Gaussian distribution is a bell-shaped curve. Okay, that is a normal distribution. It has an average. Of course, it can be pickier and all, but it is symmetric about the average of the mean value. What it means? The chances, suppose your average is say 21 years. So, chances that somebody has 20 years is same as chances 22 years. Both are symmetric, about mean. So, whatever is lower and higher have similar symmetry. This is a very common curve, and in many like natural phenomena it occurs. I just give an example of age. It is also typically true. But here it turns out Rayleigh, which is biased, which is slightly hanged on this side. This is what, of course, you may say exactly this or not. Well, actually, if you fit the graph, it might turn out to be something like some data might look like that, another will look like that, but it follows, it resembles closely theoretical Rayleigh distribution. There is a very interesting like physical reason you can think of why it is so. You see, what it means is that the chances of higher waves occurring are actually lower, okay, but lower wave occurrence is always higher. Now what happened, I always like to tell this, that see, when waves get generated when you blow wind, suppose I blow wind at certain speed, say 10 knots, wave will be created up to some height, because you have seen from physical phenomena, more is the speed of wind, more is the height of wave. Why? Because, which will come later on again. I am just trying to give you now an explanation about some kind of intuitive explanation about the shape. See, more wind blows, there are more energy to the wind, so the more of the energy gets transferred to water. So obviously the wave height has to be higher, because more energy means higher waves, because energy is height square, right? If you feed more energy water, obviously water will show up higher, wave heights will be higher. If you give more wind, obviously more energy goes into water. So now think of this, supposing I have wind up to say 10 knots, so I will have all waves. Now lower waves also be there, because lower wave can also get excited, but it will be up to some height, let us say. Now if I have 20 knots, again it will be up to probably some height. So upper bound is more or less fixed, you see, but lower bound always waves are occurring. Supposing what I am meaning, if I blow a wind at 30 knots, wind that would have been generated at 20 knot and 10 knot also gets generated up to 30 knots. So there is a pull to the lower side. You see that always the lower ones are existing more. As a result, there is a hang towards this side, you see, and this gets thinner. This is one of the intuitive reason, you may think, may not be exact reason, to tell why such phenomena are not symmetric, because here one sided, with a certain wind velocity u, waves of lower up to some height is more or less excited, not beyond that. Another wind means again lower to up, lower ones are always there. You understand? So as a result, this is more like Rayleigh. Now this makes our life very easy. If it is Rayleigh distribution, it turns out for this distribution, as you know, in a normal distribution, this function have a theoretical, like for this, it has a theoretical shape. It is given by when h bar is actually, h bar square is the, what is it, root mean square, or h bar square is, h bar is the root mean square, basically mean of the square of the wave heights, what is called RMS value, see. Which is like standard deviation. Or actually we can define this like this, h bar square then that is the probability of hi divided by whichever way you call. Essentially it is, as you know, it is mean of the square of the heights. See, you must be knowing this, that if I were to take a signal like this, now if I take an average, the average becomes 0, because plus and minus goes to 0. So that is why this idea came, to square it and then average it. When you square it, this will become like that, this will also become like that, and you get an average something. As you all know, sin theta 0 to pi, whatever, 0 to 2 pi, if you average 0, if you do root mean square, is not a 0. So that is why the idea of root mean square came, and that is why it is used more frequently rather than the mean value, because there can be a signal which is, if it goes to negative, then it becomes 0. So now if you, now the interesting point is that if you have this root mean square, then this function can be defined in terms of root mean square. Later on we will find out that this is also connected to the area of that. Anyhow, that is different. Well, that is actually the total sum anyhow. Now the question is that, it is very interesting. Then supposing statistically I have collected whole lot of data. So I have this first set of data like this. Now I have found out, oceanographer found out that most of the distribution, the histogram looks like a Rayleigh distribution. Now, I can actually figure out this particular graph by simply taking the RMS value of this signal and then fitting this graph. Okay. Then I will end up getting the shape. Once I know the shape, of course, I can easily figure out every quantity of statistical importance. For example, from if I know PHI, I can find out what is the P of H star exceeding HI exceeding H star. That will be just the area from that to this. Supposing I want to find out what is the probability of wave height exceeding this value, obviously that is this area. Okay. So, what I mean, this can be done theoretically from here. I can do it because I know H bar, so all that. Having said that, one of the most important and concept we need to tell. So, we have, see, in this signal things like H average, that is simply average. We have also H root mean square, okay, that is H RMS what we said, right. It turns out, of course, that if this Rayleigh distribution relation holds good, then H root mean square and H average are related by some constant. You can theoretically find out. In fact, what would happen that for like that the relation exists. This is all theoretical. Question is that supposing I want to signify severity of a wave, should I use RMS value, should I use average value, what should I use? Here comes a very important concept in our subject of ocean wave, which is known as H1/3, or loosely it is called H significant. This is a term that is important because mostly when you go to practice, people will tell you in single one number severity of a wave by stating its significant wave height. What is it? This is what we need to find out. Now, you see what happened. Once again, I need to draw this again. Let me again call this H's and N's. Let me just write this as this way only, say some value, say I just went to this thing and this value something, this total number N. So many. Now, what is happening? Remember what I said, there is always a pull towards the lower heights. Now, if you make an average, people felt that average does not really signify the severity of a wave or some kind of a sense of a wave. So, this 1/3 significant came, meaning of that is that from the top highest you go this side to n/3 number of waves, 1/3 of the data. Suppose there was 1000, total n was 1000. I will give example of this later on, because this is very important for any point of view. So, we need to give this example. Suppose from here I take 1/3 of the total number of waves, which is, if it is 1000, say 330, 33. Then take those waves and average it. Then I will call that to be 1/3 significant wave height. Actually, the word should be not significant, it should be called 1/3 significant, and typically I can have H1N which means what I can do is that I can take 1/nth of the total signal, okay, average it out, the highest total, not total signal, 1/nth of the highest total signal. If I average that, then it is called 1/nth significant wave height. For example, in this example only, if I were to take from the top n/10, that is 100 highest wave, average it, I would have got 1/10th significant wave height. If I did 10 waves only, I would have got 1/100th significant wave height. So, you can have all kind of H1nth significant wave height. However, by default H1/3 significant wave height is used so frequently in our subject that we call h 1/3 as significant wave height by default, although strictly the term should be h 1/3 significant wave height. And you understand, no? So, what I am trying to say that h 1/3 we call this as significant wave height loosely. And why it is used? Same thing. If I were to use, I will get a lower value slightly because there are too many waves of small heights always existing. So, it does not give a practical feel of the severity. That is why people felt it has become a custom. Actually, it is not that there is any general rule or something, it has become a custom that we would think 1/3 significant wave height to be a better measure for representing a particular wave, because that would have eliminated all this averaging over these small waves. See, small waves are always there, so many small wave and ripples. If you see any place, if you actually go to any ocean, you will find that any big wave is actually riding over ripples. You will not find a sine curve, you will find small ripples riding over there always. If you ever take a cruise or something, or go on a like ship in somewhere, you will find that the waves that you find is not very smooth, but it is always small breaks here, right, which means always the small waves are existing. So, if I count them and use them for average, the average tends to get pulled down to the lower side. You might end up getting an average of say 2.5 meter, when significant average would be 3.2 meter. As a result, the word significant wave height is more used. That is a very important concept, because in almost all of our subject we always use significant wave height, not average wave height. Now, this we need to actually like do some kind of an exercise for that. Maybe just give let us take some example. Otherwise, see 0 to 1 meter. Let us say I am just writing this again, h I am trying to work out, and this number. You can actually operate on also probability, P and I, all these are same thing. The main point is that you must take the 1/3 values and average it out from the top. Say this occur say 10 times, say 1 to 2 meter, I will just write this, or here let me write it as 15. No, actually let me take this example rather here. 0.25 to 0.75. Rather, let me take one more page. Rather, this way I will do. Average there is a frequency quotient. If I write now, let us say, so this is 0.50, say it occurs, or rather let me write the full thing down. Up to this it's here. This is 1, this is happening say 15 times. You can easily work it out to find out. See, I have a purpose for writing this, the purpose is like this. If you look at this distribution, you will find out that there is a, if I see this, I have something like 15 here, then goes to 30, then goes to 55, then goes to 21 here, 14 here, 9 here. This thing. If you see, you're going to find that it is going to be like that. It is not symmetric. You see here, peak is here, only 2 here, higher, but there is much more drag on the lower side. Now, if you see also here, number of this occurrence, this is a realistic data, very realistic data. Number of waves occurring, high ones are much lower, low ones are higher, but the lowest one is not the highest, always there is a peak. This always happens because when a wind blows, there is always a particular height that is excited most. There will be, but there are also large number of lower ones. You see larger lower ones. So, the purpose of showing that you will find that this to be bell-shaped curve. Now, here if I want to find out average, see for example, here is a question there, what is average? Very simple. Average is simply you multiply this with this etc., this with this etc. So, I will end up getting H average. Let me see how much they this thing. Well, we have to work it out. You can figure the H average value if I do that. That is 0.5 into 15, 1 into 30, etc., etc. There will be some value of H average. Let us see how much it could be. If we have a calculator, we could have done it, but let me think. I cannot tell offhand, but it is going to be something like, let us say, maybe 2 meter or so, maybe. Let me see this. Around 2 meter or so, around, if you work it out. Okay. Now, what is the, let us say from this, if I want to find out what is the probability of, for example, H exceeding say 3.25 meter or this value. This is going to be simply these numbers 5 plus 1, 6 divided by 150, straightforward. So, you can easily figure it out. This is going to be some number whatever. Now, the important point is to find out what is, how from here. Let us see this is where I want to tell you. Let us say 1/3, okay, H 1/3. How do I do H 1/3? You see here, this confusion comes sometime. I need to have the from here average of the top how many? 50. Now, count it, 5 plus 1 6, 6 plus 9 is 15, 15 plus 14 is 29 plus 21 is 50. Actually, this example that I took is becoming exactly 50. Supposing it did not become 50, for example, we will do that for 1/10, let us say we will do that for 1/10. So, here all I need to do is to average up to this much, because up to this much from here when I go to this point, I get to 1/3 of the total waves. You see, I went quite high, but I go to 1/3 of this wave. So, I just have to average this out, 4 plus 3.5 into 5 plus 3 into 9 plus 2.5 into 14 divided by 50. Okay. Yes. So, if you do that, you are going to get your average this thing. So, something like okay, up to this much, up to this much. So, it's like 21 into 2 plus, if I just put it, then 14 into 2.5 plus 9 into 3 plus 5 into 3.5 plus 4, this divided by 50. So, this is going to give you something like 2.51. But this was a very nice example. But what happened if I want to do H 1/10? You see, H 1/10 is, let us do H 1/100th, because I wanted to show you that it is not following the number. H 1/100th would be 1.5 waves in this example. Or what I am trying to say, suppose you are doing H 1/10 also, it would have been 15 waves. Now, supposing you find out that if I add this, it becomes more than 15. Let's say let me just change this number, then I make it 13, I make it 10. Okay. So if I want to do h 1/3, 1/10, what happens? That is 15. So if I go 5 plus 1, 6 plus 10, 16. What I should do? I should do 1 of this, 5 of this, and 9 of this, not 10 of this. That's what I wanted to tell you. It's not that you have to take all the waves. You have to count from here 1, 2, 3, etc. Count up to where you have 1/nth of the waves. It need not be up to this exact line. That is the one what I was trying to tell. This example, it turns out that it is falling the way it was chosen. But you have to take up to that point. You will get therefore the particular concept of h 1/3. So what is happening therefore, if I look at this diagram, it is actually average of this side, 1/3 total number from, it is the average of this heights, 1/3 of this from the top side heights is 1/3 height, 1/10 will be this side. Now so this is the concept of significant wave height. Now the interesting point is that it turns out if I were to use a Rayleigh distribution, okay, because in Rayleigh distribution I know this P of h I as a function of h bar, basically that is what the expression is. So what happened, all quantities of h 1/n can be expressed as a constant into h bar. This constant expression is available if I have a given theoretical distribution. For example, h 1/3 becomes 1.41 h bar, h 1/10 becomes 1.80 h bar, etc. like that. So what happens is, interestingly, that when I have this signal, nowadays what is happening, I will have this long signal collected, the data boys are there all over. Indian government has their satellite also, ocean sat, going around collecting data. So you will have hours of data, millions of this kind of heights. So what would you do? If I want to have a statistics, I will like another thing also I want to tell you here, that you see this average period of that is how much? About 10 seconds. If you see this time period, around 8 to say 14 seconds, say average of 10 seconds, let us say. So if I collect 1 hour of data, how much of peaks you expect approximately? Suppose I collect 1 hour of data, that is how much? 3600 seconds, so around 360. So if I collect continuously data, then what will happen? I will end up getting very large data set. So what often people do is that you cluster these things into some time intervals. For data, I am talking from the point of view of data processing. You cluster this for, let us say, every 1 minute. Then average this value and take that as a wave height. So you have then this like that reasonable number of data. What I mean, instead of taking the raw data directly, sometime what you do, taking every peak, you make time bands. For each time band you take an average, and that is taken to be the number, because otherwise what will happen, you might end up getting 1 lakh data points. So then you will end up getting something like more reasonable data points. This is a question of data analysis. Whichever way you do, you can do. Nowadays it is simpler, because what would happen, you see the digital data points are giving you this basically time versus etas, like 0. There will be what is known as sampling interval, maybe 40 second per second, 1/40th, 1/20th, depending on your system, how much of load you can take. Then it's all digitized data, and you can in a computer analyze them to find out, basically through computer only you will find out how many heights are occurring at what, etc., etc. Now having done that, you don't plot histogram anymore. What you can do, straightforward, you can find out the RMS value and go to this graph, P by H graph, and therefore plot this. That is, go to this where is this? Take a signal, figure out H bar, automatically computer will give you, then plot this because it fits more closely, and then find out for the signal all parameters like H1/3, H-RMS, etc., etc. Now, this is, having said that, what now I want to tell you. So, I have collected long set of raw data, I could statistically analyze it, I find out they follow Rayleigh distribution theoretically, that means slightly like not symmetric. I know what is meant by H1/3, H1/10, etc., but does it tell me all? Still, this is only height, as I initially told. Does it really give me the ocean characteristic? The answer is no, because I do not have the time information. For example, this signal, as I told you, I could stretch it having the height same, and the analysis will give me the same histogram. Okay, you understand the point, that what I have done is only the height I have analyzed it. What about the quantities in this direction, that is length or period? We haven't done it. Now you can say, look, I can separately analyze Tz. That also people have done. Even Tz, if you do like H, you will end up getting a graph, and this also turns out to be Rayleigh distribution. So what would happen is that, you see, we have done statistically individual quantities, HW, TC, TZ, if you want LWZ, LWC, all of them you can analyze. Normally, of course, you see, we do not collect this data, because remember, collecting this data requires you to take a snapshot over a distance, which is not done. Typically, you have a data boy located at some point, it is collecting data at that location, that is against time. So mostly you are collecting, and of course we know that theoretically length and period are connected to each other through dispersion relation. So in practice these are collected, not the length. But having said that, let us say I have a histogram for HW. Well, I know that chances of wave height exceeding 10 meter is so. I also have a histogram of TC. So I can say that chances of a wave occurring more than 15-second period is so and so. But are they not connected to each other? Can I have, you see, this information do not relate the two. For example, it cannot tell me which height and which period are related. For example, I can have a very high wave of small length or very high of large length. It will not, this analysis won't detect that, because this analysis is not going to relate to me height connected to the period. So I therefore still do not have a full description of ocean waves for a given state. As I said, that if I were to take in a randomly just two signals, if I were to take a signal, I just take an example of this and another one, I just stretch that as if it is stretched. If I were to take these two signals and do the H height spectrum, or it is not a spectrum, height histogram, answer is same. Period spectrum, answer is not same. On the other hand, for the same signal, if I just lower it down to like that, I will have period signal same, but height histogram different. The point is, therefore, we need a kind of description where your height and periods are connected to each other. Remember that period is length, therefore height and period essentially implies also the slope of the graph, because period is length. So like height and period means height and length means h by lambda means slope, steepness of the. So I need a description of ocean waves which also gives me the steepness of the graph. Now this is what we will be talking later on about how we can generate this. Now having said that, because we have still little more time, I will come to this signal process. You see here, suppose I have a random signal, never mind what signal it is, electrical analysis or whatever. What happens? Remember that you all know Fourier analysis. Actually any signal I can always represent that in terms of a series of sine and cos curves. So, we will see this concept that eta t is can be represented as series of say a I cos omega I t plus b I. Actually, I should not call it h here, let me call it to be any signal, say x t. We will see that this becomes the starting point, as we will see next class, for representing random waves or random signal as a wave spectrum. This in which the amplitude means height and the period means frequency will be connected to each other. Okay. This we will see in next class when we actually go for spectrum, but what today we learned is an important and interesting observation that wave-height distribution is not normal but Rayleigh. Therefore, I should use h 1/3 more as a and then it is being Rayleigh, everything is connected to each other. So, up to that we have learned today's class. With that I will end today's class.